And the last section in Chapter 3, we're going to wrap up the last of the derivatives. You got to learn, I think it's about 3 more derivatives here, maybe 4. But they're pretty easy formulas actually to remember. Much easier than the last section. But again, use those flashcards and you'll have no troubles remembering. If I can remember them, so can you. Today we're going to talk about the derivatives of exponential functions and log functions. So for example, if a function is e to the x, we don't have a way of doing a derivative yet. We can't throw that x out front because it's a variable. We can't do the power rule on this. We cannot do the power rule on this. So there's a new thing to memorize, and what it is about as easy as they come. You ready? Y prime is e to the x. Crazy, huh? Crazy hard to remember. The derivative of e to the x is e to the x. So therefore, down at the bottom, the derivative of e to the u would be e to the u. However, don't forget the chain. On all of these things we're going to talk about today, you got to tack on the derivative of that inside function, which is your du dx, your u prime. All right, so there's one of them. 1 down, 3 more to go. Here's a quick example of an e to the u question. If you're asked to find f prime here, you don't throw the exponent out front, folks. When it's an exponential function where you have a number as the base, and the variable's up in the exponent, this is called an exponential, you cannot throw that exponent out front. So what you do is you write, hey, the derivative of e to the u is e to the u, so I'm just rewriting it, but then what do I have to remember? The chain rule here. So we have to tack on a parenthesis of 1 plus 2x. 1 plus 2x. And there's your answer. Pretty cool. And I'm sure you're sitting there, maybe texting or watching TV or something and ignoring me completely, but you're probably wondering, well, what if the base is not e? If the base is not e, let's say it's another number. Well, it's actually not too bad here. What it is the answer would be a to the u. Well, you're thinking, well, that seems the same. Well, the only thing you need to do is put an ln of the base there, the natural log of the base. And then, of course, you're always going to tack on that du dx, the derivative of that inside function. So whenever the base is not e, you're going to put an ln of the base in there. Now, if you remember from last year, the natural log of e is 1. So really, on the previous page, there was an ln e in there. It was just happened to be 1, so we don't bother writing it. So let's look at an example using this. Here we have an exponential where the base is 5 and a function, an inside function up here in the exponent. That's our clue that this is a 5 to the u situation. All right, the formula is, the derivative is, recopy it untouched. Put an ln 5 in there because the base was 5. It was base 5, so we put ln 5. And then we tack on the derivative of x squared, which is 2x. So there's your answer. You could write it that way. All right, that wasn't too painful. 2 down, 2 to go, folks. The derivative of logarithms are next. Now this is one that you're going to need to practice with a little bit so you can spot these. And we're going to use this a lot in the second half of the year too. A lot of things in the real world are exponentials, e to the x, or they're logarithmic using the natural log. That's why it's called the natural log, because it exists out there in the natural world a whole heck of a lot. Here's the formula. Y prime is, now I want you to notice there is a function on the inside of the natural log. The derivative is 1 over u. Now I want you to notice, I've done this long enough, I know what students do wrong, and that is they put a natural log in the denominator, but the u is actually outside the log, so it's just 1 over u. 1 over u, and what do you think would go over here? U prime. U prime. That's it. So it's the derivative of natural log is 1 over u du. Let's look at an example. Let's say we have y equals the natural log of sine 2x. Natural log of sine 2x. Now, I actually forgot one thing when I was doing the formula, and I tend to be kind of sloppy about this, but the derivative is actually 1 over the absolute value of u, so you do have to slap that in there also. All right, so make sure you change your notes to that. All right, the derivative here, it's time to do the derivative, as you can hear. The derivative would be 1 over sine 2x. However, we're going to tack on the derivative of sine 2x, which would be cosine 2x. Now we have an inside function on that inside function, so we have to tack on a 2. So the answer is 2 cosine 2x all over sine 2x, which, remember, cosine over sine is cotangent. So on the AP exam, they would most definitely put 2 cotangent 2x is the best answer for y prime here. So that is an application of the natural log. All right, the last derivative. It's time to go over the last derivative that you need to memorize here. If you have a different base other than the natural log, because after all the natural log is base e, the derivative is, and again you just got to memorize this stuff, 1 over, again, u. You're going to do the natural log of a down there, gets tacked on to the u in the denominator, and then you're going to tack on a u prime at the end. You're going to tack on a u prime at the end. So 1 over u, ln a, all times the chain, which is u prime. So here's a quick example. This stuff really is not that hard once you just memorize these formulas. The derivative is going to be 1 over the inside function here, which is 10x plus 2. You got to tack on a natural log of 5, because that comes from this base right there. And then you're going to tack on the derivative of the inside function, which is going to be where a 10 over 1 comes from. So a decent answer here would be 10 over 10x plus 2 ln 5. You could actually factor a 2 out of the bottom, which isn't a bad idea. ln 5, and then 2 goes into 10 5 times. So you could cross these out and maybe have this as your answer. 5 over the quantity, 5x plus 1 times ln 5. And that's pretty much the best you can do is simplifying. All right, we're almost there, folks. Throughout this chapter, we keep using the power rule, and throughout this chapter, they keep sort of adding to it, just saying, hey, you can still do it. We learned we could do it with an exponent of 3. Then we learned we could do it with an exponent of -4. Negative numbers are 5. And then we learned we could take the derivative of x to the 1/2. We just throw the 1/2 out front. Well, guess what? You can actually take the derivative using the power rule, even if there's like an irrational number like pi or the square root of 2 up there as an exponent. So here's an example. We would be asked for the derivative. We would throw that exponent out front because here it is just a number. It's not the square root of 2x or anything. It's just a number. So we throw it out front. The base stays the same. We've been saying all year long. The exponent goes down by the number 1, which would be, I'm going to write it this way, -1 plus the square root of 2. And then we would tack on the derivative of the inside function, which of course is just 1 here. The inside function is just x to the first. So that's your answer. Square root of 2, x raised to the radical 2 minus 1 exponent. Now that's 1.4 minus 1, which is 0.4. But let's just leave it like this. So either of these are really great ways to write this. All right, so here we have a skill. This is a way to do a derivative, a skill. It's not memorizing a derivative. It's how you might have to take a derivative, and it's called logarithmic differentiation. Really big words. Say that 3 times fast. Logarithmic differentiation, logarithmic differentiation, logarithmic differentiation. All right, I know you think I've gone over the deep end, and I think I have, but we're going to go ahead and recognize that this is a y equals statement. And over here, look at this. This is nothing we've talked about today. We have an exponent as a base, and crazy, there's an exponent up in the exponent. So we cannot just throw that 2x out front. When there's an exponent up in the when there's an x up in the exponent, we can't use the power rule anymore. All right, so well, how are we going to do this? We're going to take a log on both sides, and I think maybe we did this a little bit last year, not taking the derivative, but putting logs on both sides is a legal move. So we now have, and I just use natural log because I like it, natural log y equals. Now, you remember one of the properties of logarithms is that you can throw things out, you can throw exponents out front. So this guy can now be safely thrown out front because that's just an algebra move. That's not calculus. So now we have 2x natural log x. 2x natural log x. And I'm going to put a dot in between there because, we're going to have to do the product rule when we actually apply the calculus. Now, let's take the derivative of both sides. This is called implicit differentiation. You remember that from 3.7, implicit differentiation. The derivative of natural log y is 1 over y, but we have to tack on a y prime because we're taking the derivative of something with y in it. Equals. Now we have to do the product rule. The first times the derivative of the second plus the second times the derivative of the first would be 2 natural log x. The derivative of the first is 2. All right, we then solve for y prime. So y prime is, these x's happen to cancel, so we're going to have y times the quantity 2 plus 2 natural log x. 2 plus 2 natural log x. Now remember from the original problem, you might think we're done, and we're just not quite there yet. The original problem said y is the same thing as x to the 2x. So what you do is you stick that in right there and you say my final answer is x to the 2x times the quantity 2 plus 2 natural log x. There's the derivative, and we used a method called logarithmic differentiation. How do you think they came up with that name? They're putting a log on both sides before taking the derivative. Before doing the calculus, you set yourself up for success. It creates a product on the right side, and then you could just use the product rule. All right, that's all, folks. I guess I should have the Warner Brothers theme playing right now, but those are all the derivatives that you need to know. In Chapter 3, you started out with the power rule. We went through trig functions, inverse trig functions. Now we did exponentials and logs and all these great things. We learned about implicit differentiation. We learned about the chain rule. It just went on and on. But the good news is we're done learning derivatives, and in Chapter 4, we then use them to do very cool things like, for example, find the best place to operate a business. How many widgets should you create? If you want to minimize cost or maximize profit, you use calculus to do that. And we're going to be using derivatives. So good luck on your homework. Be ready for a test over Chapter 3 also. Good luck.